Hi, everyone. Welcome to December's community call. We're really excited to be able to cover the alpha release for cadCAD Reference that is open now, and you can start playing with it. And so we'll cover about how to get started there on this call, and then we'll give the floor to Emanuel to do a bit of show and tell and demonstration of what this current alpha release can do and how you can get started, and then we'll have a bit of Q&A afterwards. So before we get into all that, just like quick agenda setting, covering all the updates from the other groups as well. From the infra admin working group, we've got, which meets every Tuesday, 5 p.m. UTC. We've got in the works cadCAD Wiki. We're currently testing workflows between Discord forums and GitHub, and building up documentation to support cadCAD Reference. We also have a bounties program under development. The updates on that are we're working with ossgrants.com, and we see that these bounties would be paid in XI through a Gnosis multisig, and this is all, the program is building on top of the work that OSS Grants did with TEC and NumPy to build out a program there. We're looking into just setting up a simple application process to just have identified known contributors. It makes the pay scaling easier. We've discussed this in previous calls. And it helps us figure out how to specify bounties going forward. And eventually we want to move towards proposals and away from bounties issued centrally from the cadCAD Foundation. But we see bounties as a way of instantiating the program and instantiating the community around this. So we're really excited about that and targeting early 2023 to have that launched and running. What we have to do on this at the moment is getting the contributor guidelines documentation in place and finalize, getting GitHub teams set up, issues, repos, flows to support all this and getting it all sort of hooked together. And then determining how we want to raise additional funds for specific proposals. That's, I think, a little bit more TBD. But we're not blocked on any of those. And so on the core tech working group, which meets every 2 weeks on Wednesdays, 5 p.m. UTC, the next core tech call will be next Wednesday. And so that's the group where we focus a lot of time and energy on cadCAD Reference. And so as a roadmap and progress overview, spaces is completed, points, blocks, trajectories, and chain of blocks. And under chain of blocks, you see SISO. This stands for single input, single output. This is important because we're calling the current alpha release SISO Alpha to stand for you can run models with SISO blocks. And then what we are working on is block piping language for doing compositions. We'll have further down the queue some experiment support tools and orchestration tools. So to get a little bit more granular, and this is more about how blocks are constructed with different input-output parameters to them. So eventually what it will look like is, I'll just go to the next slide to get this in more detail. Multi-input, single output, and so that'll be decorator based, and that's in progress. And then a hybrid composition, which will now support single input, multi-output. And this will be under the overall umbrella of canonical GDS, a generalized dynamical systems. There is a second GDS white paper that will be published pretty shortly that Zargam and Jamshid are working on. And this will be the second of, I think, 3 that they're planning for the series. And we're also working on the domain-specific language composition tooling, which is a way to do a block piping language so you can specify how blocks are piped. Then further down the road will be beta. So we'll have some subsequent alpha releases. And then beta, we're targeting for April 2023, public beta And with this, we will want to also get parallel composition, which gives us multi-input, multi-output. And so then by beta, we'll have supported single input, single output, single input, multi-output, multi-input, single output, and then with beta, multi-input, multi-output. So then you can basically model any sort of system you want with these block compositions. So let's just get into some specifics about composition tooling, domain-specific language. What that really means is it's a small formal language. We're just trying to get syntax and semantics for the pipelining to get together. It'll support serial and parallel compositions of any blocks, and that's how we get to support all the different sort of input-output types. We want it to be a modular syntax and grammar, where you have meaning at the sort of bit level and as individual strings, and then you build meaning on top of that. And it's going to be agnostic from the Python implementation for reference or the Rust implementation or the Julia implementation. So this language will be unique to the cadCAD sphere. And part of this is it'll help reduce uncertainty around what the rules of the block pipeline are, and because it's going to get down to the compilation level, and we can from that point ensure the validity of points on the spaces of the dynamics that are being put together. And the other nicety of this is that it really facilitates building tooling on top of the cadCAD engine here. So we can build visual cadCAD, which I think has been teased in the past, where it's a GUI-based cadCAD builder, where you can write block diagrams, and then that gives you a cadCAD model. And so with the DSL here for composition of blocks, in a visual cadCAD, what you could potentially do is something like you build your block diagrams, and then under the hood, it's writing the block pipelines for you. So this is extremely important. It's very exciting. And it will just bring the ability to build cadCAD models just to the next level. But what we have now is a working release of cadCAD reference. So under the SISO Alpha, this is an example of what a model in reference can look like. Emanuel will get into more in depth on this, but this is just sort of a primer of how things will look. So if you wanted to get started, you can go right to the repo in the development branch right now. I think in the coming weeks, there might be a little bit of reorganization around that, and it will be very, very clear and spelled out in the cadCAD RI repo of where to find whatever you're looking for. And we have examples, if you want to play with examples first, under the docs folder examples in that same repo. So that's what we have on sort of prepared slides. I want to hand it over to Emanuel to do a little bit of a show and tell.
All right, I'm going to share my screen.
Awesome.
Okay, so basically, there is a notebook that you guys can find on the docs folder of the cadCAD dev branch. All right, there is a docs folder where the whole documentation is going to live, and in the future there is going to be a pipeline to pick documentations on this folder. There's going to be like markdown files and stuff. This is just a curiosity. And then it's going to transform this into a documentation website for cadCAD. But that's a little bit into the future. But right now we have some example notebooks on this folder, as we don't have a proper documentations website yet. So there are a lot of notebooks here. that were mainly written by Michael Zargam, who is helping us more on the requirements and formal aspects of cadCAD. And I'm going to go through you guys a short notebook, and then I'm just going to open to questions. Not going to keep talking here for like many minutes on end. So to just jump right in. So basically, there are three basic concepts on cadCAD reference implementation. Basically, we have the concept of, I'm going to write this down here, and then I'm going to erase this. So basically, we have the concept of spaces, all right? We have the concept of the blocks, and we have the concept of points. So basically, those are the three main concepts that a modeler is going to interface with in order to make simulations in cadCAD. So first of all, the first concept, the first construct one will have to declare when starting a cadCAD simulation are the spaces. And the spaces are basically just a contract that describes the types that make up the world I'm trying to simulate, right? So basically, at the top of the Python script or Jupyter Notebook, I'm just doing like regular inputs here. So this is nothing like weird. So from like cadCAD spaces, I import space, and from Dynamics, I import the block stuff. From spaces, I can also import some built-in spaces that we put for ease of use, and for points, I import points, and that's pretty regular stuff. What really matters is the declaration of the space. So as I was saying, you declare the space to describe the world you are modeling. So in this instance, Zargam was modeling a Cartesian plane. And a Cartesian plane, so his whole world was a Cartesian plane, and the Cartesian plane is basically comprised of two floating point numbers. And each of those has a name associated to it. In this case, Zargam called it X and Y. What this means is that the syntax for spaces is basically at space, because space that you import, for example, on this first line here, this space here, is a decorator. It's a decorator for classes. So the space is a decorator for classes, and then when you pass a class for that space, that class will have to have a set of attributes, and those attributes will have to be typed, right? So basically, I call the decorator, I construct a class, I put the attributes. Those attributes must be names, a column, and then the type. So here, two floats. But those can be like any types. So any Python types that one is accustomed to using, like for example strings, integer, floats, or whatever. Or it could also be types that come from other libraries. For example, a numpy.double, for example, a type that is like imported from numpy, from another library, or it can be another space. So if Cartesian plane is a space, I could say that Y is our Cartesian plane like so. Okay, of course, it cannot be recursive like I'm doing here, because at the time of evaluation of this Y here, Cartesian plane does not exist yet. So it should be a space that was declared before, ahead of time. But because a space is also a type, it can also be the type of an attribute of another space, right? And this is a very important point. A space is a type, and as such, a space cannot be instantiated. So it's different. It comes from a Python class, but it's different from a Python class because you cannot instantiate, you cannot create an object from a space like you could with a regular Python class. If Cartesian plane was a regular Python class, I could just pick values for X and Y that like, and because Python is a dynamic language, it wouldn't even need the values to be floats. It would initialize with any values. But like if you try to instantiate spaces, it's going to throw an error because spaces are just types. They live as types and they do not give birth to actual objects. On this following line here, this is just an example of some of the rich API that spaces have. So even though spaces are types, we were able to provide a lot of machinery for spaces. So spaces, they are types, but sometimes they behave like objects in the sense that I can dot something a type. So this would be something as crazy as doing in Python, for example, int, there is a type, and dot, I don't know, name like so. It's like if I was asking a function, an action from a type, right? This is, of course, not valid Python because types in Python do not have actions, but in cadCAD they do. And so this line here is basically just renaming the attributes, or rather, as we call it, like technically, the dimensions of the space Cartesian plane. And when I rename, I have to pass a dictionary where the keys of the dictionary are the old names and the values are the new names, and they must all be strings. And when I execute this, Cartesian plane dot, that is the result of this computation here, is going to return another space. So it's a copy. So spaces are never changed in place. Okay, so rarely they are changed in place, at least. And so when you, for example, rename the dimensions, all of the names of the dimensions that you changed are going to be the new dimensions of the new space you are producing, and those two spaces are going to be separate. This new space is going to be called Cartesian plane dot, and it's going to be completely different from Cartesian plane. And both of them are still going to be available on the namespace. And then there's a lot of other APIs you can go on the root of the repository on the dev branch. Inside of the cadCAD folder, you go into spaces.py where there is the actual declaration of the logic of the spaces. And if you go inside of the actual decorator, the space decorator, all of those functions here are exactly the APIs for all of the actions that that a space can do. So I can ask for the dimensions of a space. I can do like Cartesian products. I can do power. I can ask for the name. I can ask for copy. I can rename the dimensions as I showed. I can ask if it's empty or not. I can unroll the schema, and I'm going to explain a little bit what unrolling a schema is. I can do addition, I can do nesting, and I can ask for equivalence. So basically, all of those are the actions that we do on spaces. And if you, of course, if you guys are curious about how we implemented all of this, because we did some forms of magic to actually empower types with actions, you guys can take a look here. There is the whole like implementations. Some of them are quite simple, others are somewhat confusing for the actions that we provide spaces. Anyway, so about the unroll schema stuff, basically, because I can have spaces inside of spaces. So for example, on this Cartesian plane here, I could have a Z attribute that is called, I don't know, a space real. And real is a built-in space that you can import. For example, here we import real. And real by itself is just a space whose only attribute is a float number. It's a floating point number. It's a real number. So I can put spaces as attributes of other spaces. And that is basically nesting spaces one inside of the other. So when I do unrolled schema on a space, I just substitute, instead of real here, I substitute this real for the attributes that actually comprise real. So it would be float. So I like unroll all of the attributes of spaces, like recursively, into their constituent types until there are no more spaces to be recursed on. So until I'm left only with built-in types or types that come from imported libraries, meaning types that are not spaces, right? But that's basically what unrolling does. And then on here, on this next cell here, just Zargam just declared another space, and that space has attributes like position, velocity, and max speed. And like I told, like you could put spaces inside of other spaces. So this space particle has Cartesian plane, that is another space inside of it, Cartesian plane dot inside of it as well. So that's like the first, one of the most important aspects of cadCAD, that's space. So now to blocks. So basically blocks are those two cells here are blocks. So blocks are the logic or the action that is going to transform, that is going to make the simulation go forward. Like, so that is going to transform data. It's the logic that is going to transform data, basically. So remember that even from cadCAD Legacy, you have like basically on all like time-dependent simulations, you start from a starting point, and then you iterate on that starting point repeatedly based on some rules, right? And then on each step of the simulation, on each step of time, you update the you actually update the that for example the position or the state or whatever in time according to some rules. So on cadCAD reference, we call those rules the blocks. And the point that we are now is that we can execute with cadCAD what we call SISO blocks. And SISO blocks are basically, it's just a fancy name to say that those are blocks that receive 1 point and output 1 point. There are other kinds of blocks. For example, there are blocks that accept 1 point and return multiple points, or accept multiple points and return just one or other multiple points. But for now, on cadCAD, we have like the basic case that we can do simulations where a certain block, and you can think of block as a Python function because that's exactly what it is, that accepts a point, or you can think of a point as a piece of data. So it receives one piece of data and returns another piece of data, right? So about points, that's important before continuing about blocks. About points, a point is just like from a programming perspective, a point is just a Python class, right? But a point has two basic attributes, two very fundamental attributes. The first one is the space where that point pertains to. So a point always belongs to a certain space. All right. And the data inside of that point, the data of that point, must conform to the shape of that space, to the attributes of that space. So for example, if we go here on this Cartesian plane here, how would we go about constructing a data for that Cartesian plane space? So a point in the Cartesian plane space would have data, and data in Python, at least on the Python implementation, is always a dictionary, right? And then the data would be something like this. Because we have x and y, we would have x. And this x here, it would be, for example, 3.4. And then we would have a y. Sorry, we would have a y. And that y would be like 4.5, right? And that data would conform to the space Cartesian plane because the individual data that are inside of this dictionary conform specifically to the data that is declared inside of the space, to the attributes that are inside of this space here. So we say that x is a float, so inside of the data, x is a float. We say that y is a float, so y here is also a float. Okay? So this is okay. On the contrary, if y here was the number 4, this would be bad. This would be bad. And if we try to create a point in the Cartesian plane with this data 2 here, I'm going to call it this data 2, cadCAD will throw an error because this does not make any sense. Okay? And this would not make any sense because y is not an integer, y is a float. And basically, the syntax for point, I would say my point, and the name doesn't matter, but like my point is like point well, and max speed is just a float. So this becomes unwildly very fast. So we are trying to find ways to make this process like a little bit better, right? We are thinking about UX sugar, because if you have like, I don't know, 5 levels deep spaces, this is going to be like a 5 levels deep dictionary. It's very, very bad for modeler to write this by hand. So we're thinking about syntactic sugar for that, but that's for the future. So basically a block is the action that is going to transform points. So what I do is I pick up a point, this first block here, and this point is on space particle, and then I return a point on the space bit. And the space bit is just a space whose only attribute is Boolean, right? It's either true or false. Anyway, and then Zygam writes his own logic here. That's not important for syntax, but basically the block is also a decorator that I import here from Dynamics. Okay. And then a block is a decorator over Python functions. And I pass a regular Python function declared with def. And that function must return what it says it returns here, right? A point of a space. In this case, bit. Right here on the cell below, we have another block. And that block receives a point on particle and returns a point on particle. So I think about, and that's basically what blocks are. So there is a very important point here about concatenation of blocks. So the whole thing about cadCAD is, and what we can do right now, is that we can concatenate blocks. And by concatenating blocks, we can produce arbitrary pipeline of blocks that means arbitrarily complex simulations. So imagine I start my simulation, I start with a point. Let's imagine I start with a point on the space particle. Okay. So if I start on a point in particle, I have to start my block pipeline, my concatenation of blocks, with a block that accepts a point in particle, right? So I can either start with project valid particle or is valid particle. So like that, let's not worry about what each of those blocks actually do. So that's not important. Let's just focus like on what the interface for each of those blocks are. So if I start with a point in particle, I can either do project valid particle or is valid particle. But the problem is, if I start with is valid particle, if I do this, I will never be able to put project valid particle after is valid particle, because what is valid particle outputs is a pointing bit. If is valid particle right here outputs a pointing bit, that pointing bit cannot go into project valid particle because project valid particle only accepts points in particle. So if I try to shove a pointing bit inside of this block, cadCAD is going to throw an error. So what I have to do is, on this very contrived example, is I have to do my pipelining like this, right? So I start with a point particle. Let's say that this point in particle is my initial stage, for example. And then I put that initial stage through a project valid particle, all right? And because project valid particle accepts a point particle. And that block returns a point particle as well. And that point particle is accepted by the following block, that is valid particle. So right here, after this whole pipeline, a point in bit is returned, right? And this is a valid run of cadCAD. This is not a simulation yet. This is not what people call a dynamic yet, but this is a valid run of a cadCAD model. So what happens is, if I start from a point particle and I stop at a point bit, this is not a proper dynamic or a proper cadCAD simulation. And to actually have a proper cadCAD simulation, I would have to have a block that would accept a point bit and return a point particle. So I'm going to say from bit to particle, or whatever, from bit to particle. And let's say that this block like magically transforms a bit into a point particle. Sorry. Now, and then I finished with a point in the same space, I now have a dynamic. And because I can produce trajectories, because a trajectory is exactly a set of points in a certain space. So if I repeatedly, for example, 200 times, or rather for 200 times steps, execute this whole pipeline of blocks here, minus this point bit, because point bit is not a block. If I execute this whole pipeline here 3 times, or 200 times, or 500 times, I will have a trajectory full of points in the particle space. And that is going to be my, that would be the end goal of my simulation, the end product of the cadCAD simulation. But the main lesson here is that for block concatenation, be it a SISO block, be it a MISO, SIMO, or MIMO blocks, that those are the other multiple blocks we'll have in the future. The basic rule is, if I want, those are like Lego pieces. So if I want to fit 2 blocks, the output of the previous block must be the same as the input of the next block. Or in more technical language, as we say, the codomain, that is the output of the previous block, has to be equal to the domain or the input of the next block. So in that way, there is a complete data flow from one block to the other. So that's where we are right now. So we can do like a pipelining of SISO blocks, because we can flow data on the pipelining of blocks, but just of singular points. And then what else is important here? This is just a bunch of blocks that Zargam defined. And so here he actually defines a point, a standalone point. And like I told you guys, this because we have nested spaces, this becomes like quite convoluted. So we have like pose here with another dictionary because it's a space. and val here with another dictionary because it's also space, and then max speed is just a float because max speed is just a float. So you can imagine if we have like 3 or 4 nested spaces, it's going to be like unwieldy. But anyway, so init Alice is basically a initial space, a initial point for the simulation. And then I declare a dictionary, and this is somewhat similar to what we do in Legacy. And this is probably going to change in the future. So this is very like early days for the experiments. So we declare an experiment parameters, and that experiment parameters, meaning how many times the whole simulation is going to be repeated, and the number of steps, meaning how many times steps each simulation is going to run for. And then once we have those experiment params, we are going to need a experiment object, and we declare the experiment object like so. We have like an experiment constructor. We pass the initial point, meaning init Alice. We pass the parameters of the simulation, these experiment params. And then we pass a tuple of blocks. Right now, this is a tuple of blocks. So, for example, I can do on this example here can be like all of those here, like those with commas instead of arrows. I have put arrows here because once we have the DSL, the DSL is actually going to substitute this tuple. I have put a tuple because we can only do SISO pipelines, and because they are SISO pipelines, there are no like there are no ambiguity on how we are going to concatenate those blocks, right? So basically, the last thing we have to pass experiments is the tuple in order of the concatenation of the blocks. And then you just ask my experiment to run, and that will produce a result matrix, right? And then with that results matrix, you can like do whatever you want. It's going to be a matrix where each line is a run. So because of these experiment params, it's going to be a 5-line, 25 columns matrix, basically. And that's the end of a very basic cadCAD simulation, actually. So I encourage you guys to clone the repo and try to execute this notebook. I'm not sure I can execute this now because like I am not on my regular working machine. So I don't have like the whole thing ready. But I really encourage you guys to test, to try to you guys can like work from this model, use this as a skeleton to see how a model behaves, to see if anything breaks. I would ask you guys to try to break as hard as you can the library and to open issues at the repo if you guys have like suggestions to improve UX, or if you guys have bug reports or, or any other. And I mean that not only like bugs, actual bugs in the engine that explode everything are issues. If you guys have questions about UX, I also see UX as a bug, UX problems as a bug. So if you guys have, for example, this thing of declaring points manually for very nested spaces, that's a UX problem, and I see that as a bug. So if you guys see any other UX problem, please let me know. Open issues on the GitHub repo, and if you have any questions, just call me on Discord.
Yep. Thank you, Emanuel. Yeah. Part of why we're excited getting this CISO Alpha out to the community and being able to basically play test it and like just pound on it as hard as possible is it'll give us feedback on how to do subsequent releases as we approach beta. We can only dogfood it so much, and when you look at something every day, you get a little too close to it. So getting an outside perspective at this juncture is invaluable to cadCAD reference. So we appreciate all the community input we can get. Before we wrap up the community call here, does anyone have any questions or follow-ups they'd like to get from Emmanuel now that we're all here? Cool. Well, I guess on that note, thank you all for coming, and thank you, Emmanuel, for just like diving really deep in on what CISO Alpha is, and
All right. Thank you, guys.